Pre-statistics. Using the quadratic formula to solve quadratic equations, Part 4. Lesson objectives. Use the quadratic formula to make predictions with a quadratic model. Lesson objective. The annual consumption of bottled water in the United States have been increasing since 1990. So we have our table here, and as the years increase, the consumption has been increasing. Let F of T be the bottled water consumption in billions of gallons in the years that is T years since 1990. A possible equation of F is F of T equals 0.016 T squared plus 0.12 T plus 2.18. Number 1. Verify that F models the data well. Number 2. Predict when the annual consumption will reach 11 billion gallons. Number 1. Using a graph and calculator to construct the scattergram, or sometimes called a scatter plot, we see that the model is fitting the data well. So we can use this equation to make predictions. So we take our model, we set it equal to 11 because we are wanting to know what time will it reach 11 billion. Since the units are billion, F of T will be 11. Next, we need to put this in standard form, so we subtract 11 to both sides. Now this is in standard form. This is A, this is B, this is C. Using the quadratic formula, we have T equals negative 1.2 plus or minus the square root of 0.57888 divided by 0.032. The square root of 0.57888 becomes 0.7608. Approximating this, we have T as a negative 27.53, or T is approximately equal to 20.03 to 2 decimal places. Let's verify these solutions. We put the equation in y1, and using the table feature, when x is a negative 27.53, we have something very close to 11, and when x is 20.03, again we have something very close to 11. So what does this mean in terms of the problem? Well, negative 27.53 corresponds to 1962, because T is the number of years since 1990, and 1990 minus 28 is 1962. 20.03 corresponds to 20 years beyond 1990, which is 2010. The estimate for 1962 is a result of model breakdown. We predict that it will be 2010 when the bottled water consumption reaches 11 billion gallons. Example 11. An object thrown or fired straight upward at an initial speed of v sub 0 feet per second will reach a height of h feet after t seconds, where h and t are related by the formula h equals negative 16 t squared plus v sub 0 times t. Suppose that a bullet is shot straight upward with a initial speed of 800 feet per second. Number 1. When does the bullet fall back to the ground? Number 2. When will the bullet reach a height of 6,400 feet? Number 3. What is the height of the bullet at 20 seconds? Number 4. At what time does the bullet reach its highest point? Number 5. How high is the highest point that the bullet reaches? Solution. When does the bullet fall back down to the ground? We are asked to find the time when the height is 0. So we know h is 0. So we are looking to find point E. Substituting 0 in for h, we need to solve for t. This is in standard form, so A is negative 16, B is 800, and C is 0. Substituting these values in the quadratic formula, we have negative 800 plus or minus the square root of 800 squared minus 4 times negative 16 times 0. So this quantity becomes 0. So we take 800 and we square it, take the square root of that, and then divide everything by 2 times negative 16. The square root of 640,000 is a perfect square. Turns out to be 800. So we have negative 800 plus or minus 800 divided by negative 32. Negative 800 minus negative 800 is negative 1600, and 1600 divided by negative 32 is a positive 50. Negative 800 plus 800 is 0. 0 divided by negative 32 is 0. So our t-intercepts happen at 0 and 50. So in the terms of this problem, we would say at 0 seconds and at 50 seconds, the height of the bullet is 0. Number 2, when will the bullet reach a height of 6,400? We're asked to find the time again when the height is 6,400. So in this case, h is 6,400. Substituting that into our quadratic equation, subtracting 6,400 to both sides, we now have this quadratic. The value of a is again negative 16, b is 800, but in this case c is a negative 6,400. We substitute these values into the quadratic formula. Order of operation, we have to compute what's inside the square root first. So we first have to square, then we have to take 4 times negative 16 times negative 6,400, then subtract, and then take the square root. So we have 640,000 minus 409,600. Subtracting those two, we get 230,400. Believe it or not, that turns out to be a perfect square. Use your calculator, and we see that the square root becomes 480. Negative 800 minus 480 is negative 1280, and divide that by a negative 32, we get a positive 40. Negative 800 plus 480 is a negative 320. Negative 320 divided by a negative 32 is a positive 10. So at 10 seconds going up and at 40 seconds going down, the height of the bullet is 6,400. What is the height of the bullet at 20 seconds? We're asked to find h when we know t is 20. Substituting 20 in for t, we square, then we multiply, and finally we add, and we get negative 6,400 plus 16,000, which is 9,600 feet. So at 20 seconds, the height of the bullet is 9,600 feet. Number 4, what time does the bullet reach its highest point? Whenever we see find the highest, or find the maximum, or find the lowest, or find the minimum, that is to tell you to find the vertex. Because we are wanting to find the time, that is the x coordinate of the vertex. So we know that a is negative 16 and b is 800, so using the axis of symmetry formula, negative b divided by 2a, we have negative 800 divided by 2 times negative 16. Negative divided by negative is positive. We see that x is 25. So at 25 seconds, the bullet reaches the highest point. Number 5, how high is the highest point that the bullet reaches? What is the maximum height? That is the y coordinate of the vertex. So the x coordinate is 25. We substitute 25 in to the function, and we see that the maximum height is 10,000. So the vertex is 25, 10,000, and in the terms of the problem, it means at 25 seconds the height of the bullet will reach a maximum height of 10,000 feet. Let's verify this on our graphing calculator. I have the equation in y1. And of course, if we hit graph, we're not going to see anything in the viewing window. We need to adjust it. We know the x-intercepts are 0 and 50. So for the x-min, I'm going to use -10 so I can see the x-axis. For the x-max, I'm going to use 60 because our second x-intercept's at 50. And I'm going to count by, let's say, 5. For the y-min, well, we had a maximum y value of 10,000. So I can see the x-axis. I'm going to use a -2,000. And my y max will be 12,000. That way I can see the vertex. And I'm going to count by, let's say, 1,000. We'll see what this looks like. Hit graph. Okay, here we can see, here's the x-intercept, the y-intercept going through the origin. This is the second x-intercept at 50. Here's the maximum happening at 25 at a height of 10,000. And if we go to calculate and number 1 for value, when x is 0, y is 0. When x was 10 seconds, we had a height of 6,400. At 25, we have a height of 10,000. That is the maximum. At 40 seconds, again, we had a height of 6,400. The bullet is coming down. And then finally, at 50, we have a height of 0. So the domain of this function in the terms of this problem is the time 0 seconds to 50 seconds. The range, the height, ranges from 0 feet to 10,000 feet. Thanks for watching.